Section 2.3 is called Characterizations of Invertible Matrices, and this section centers around what our textbook calls Theorem 8, the invertible matrix theorem. We're going to look at a whole bunch of statements that are equivalent to each other in the square matrix case. It's really important here to realize that we are talking about a square matrix only. A has to be n by n. If the number of rows and columns do not match for a matrix, this theorem does not apply. This is only for square matrices. And the way the logic works here is that each of these statements in this list are equivalent. That means if any one of the statements is known to be true, then all of the statements must be true. Up a bit. Now, I'm going to break this video lesson into several parts. The first part will be just talking about the theorem. In the second part, we're going to prove the theorem. And in the third part, we'll do a few problems. So in this first part, we're just going to talk about what this thing is saying. So the first statement is A is an invertible matrix. So remember, n by n, a square matrix. That means A inverse exists. The second statement is A is row equivalent to In, the n by n identity matrix. Third statement is A has n pivot positions. Statement D, the equation AX equals 0 has only the trivial zero vector solution. Part E, the columns of A form a linearly independent set of vectors. Statement F, the linear transformation that takes x to AX is 1-to-1. Statement G, the equation AX equals B has a solution for every B in Rn. Then we have H, the columns of A span Rn. And finally I think it fits onto the screen here, the linear transformation that takes x to AX maps Rn onto Rn. Now the textbook actually even has a few more parts to this, but I think we have enough right here. What do we have? 9 of them. So I'm going to leave off the last few that are in the textbook. And so A is invertible means A inverse exists. And we've seen for a square matrix, either there is an inverse or there isn't. By the way, if there is not an inverse, if A inverse does not exist, then each one of these statements is false. So this is also saying something about a matrix when it does not have an inverse. Notice that I think of these statements as being of 3 types, and I like to group them together. I like to group A, B, and C together because they're saying very similar things. If matrix is invertible, our technique that we developed in section 2.2 involved using the fact that A is row equivalent to In. And it also should be pretty clear that if we're row equivalent to In, then A has n pivot positions. So the equivalence of those 3 shouldn't be that surprising. I'm also going to group D, E, and F together because we've already seen in chapter 1, near the end of chapter 1, the equivalence of these 3. AX equals 0 has only the trivial solution, and the columns of A form a linearly independent set if the linear transformation that takes x to AX is 1-to-1. Those are characterizations of one-to-oneness. And also, it helps if you can group G, H, and I together because we also talked about how these statements are equivalent in chapter 1 also. The equation AX equals B having a solution for every B, the columns of A spanning Rn. Those are different ways of talking about the onto-ness. Those are all statements about onto. The previous three are all related to one-to-oneness. What is really surprising, one thing surprising about this theorem is that it involves an equivalence of one-to-one and onto-ness for these linear transformations from Rn to Rn. So if the matrix is square, if the transformation has a domain that has the same dimension as the codomain or range space, then the transformation has to be either both one-to-one and onto, or neither. If the matrix was m by n, if the number of rows and columns were different, we've already seen examples where you can have one-to-one without being onto, you can be onto without being one-to-one. But what we're now seeing in this theorem is that if the matrix is square, one-to-one and onto go together. You must either have both or you have neither. So I'm going to end this portion. In the next video, we'll actually work through the steps of the proof of this theorem.